Hey everyone, today we're going to be looking, sorry that was really fast, but today we're going to be taking a look at the confidence interval for the slope of a regression line. This is section 12.1, day 2. And just as a quick refresher, remember that we're talking about the slope of a regression line, and we're trying to see what are all plausible values for the true slope of the linear relationship. So let's go ahead and take a look at what we have with our worksheet. Okay. If you remember from yesterday, we were talking about, do students who sit in the front row do better than students who sit farther away? We had a sample of 30 students and we found these results. The line of best fit was 84.45 minus 1.5 rho. And actually, if I remember correctly from yesterday, I got the numbers a little bit wrong. It should be 85.95 minus 1.5 multiplied by the rho. So, starting off, what is the value of B? And we did a little bit of rounding there, but negative 1.5 is what our value of B is. Next to that, we see SEB. And SEB is a standard error for the slope of the line. Basically, if we did a whole bunch of random arrangements of these scores into the different seats, then each one of those would vary from the true slope of the line by about 1.33 units per units. So question 1, a little bit of a review. If Mr. FERRERIA were to take another random sample of 30 students, do you think the slope of the LSRL would be the same? Why? And really, why should they have the same slope? We are rearranging the students and their scores around so that basic relationship between the scatter plot is going to be different. And we're going to create a different LSRL. And because it's a different LSRL, it'll have a different slope. That's a little bit of sampling variability. Now, number 2, we're going to construct a 95% confidence interval for the slope of the population regression line. The population regression line is the true regression line that relates rho to score. So we're going to have to identify the parameter and statistic. You might think that this is very similar to the state part, and well, this is a state part. This one's a little difficult to fit on that blank, but beta 1 is the true slope of that population LSRL. Remember, LSRL is synonymous with regression line as far as AP statistics is concerned. Now, the statistic would just be the approximation of beta 1. So our statistic is B, and it's negative 1.517, which is the full unrounded number that we found from here. So that is our value of B. Now, there are 5 conditions to check, and maybe we should start off with the name of this test. The name of this test is a 1 sample t interval for beta 1. Now I'm typing out the word beta 1 instead of using the beta symbol, just so that we can get used to pronouncing that the correct way or saying it the correct way, which I guess is relative because there are plenty of the world that calls that beta, I think. Anyways, there are 5 conditions that we need to check. They are linear, independent, equal standard deviations, and random. And I'm highlighting here so you can see that this is an acronym that we're going to use. It is the acronym LINER. Admittedly, not the best acronym, but it's at least it's descriptive. This is about a line, so LINER. So, what are the conditions? Well, number 1, the scatter plot needs to show a linear relationship, And also the residual plot shouldn't have a leftover curve pattern. So let's take a look at the scatter plot first. We got to make that kind of small so we can fit it in here. And yeah, that scatter plot doesn't look like it has anything but a linear relationship. I know we've talked at great length in class about this, but in general, there is a negative relationship between the row number and the test scores. Now, what about that residual plot? Well, here's a look at the residual plot. We'll zoom in here, and we can see that there isn't a curved pattern to this residual plot. So we are okay with L, the linear aspect of these conditions. Secondly, independent. And remember that for independent, the second step, basically we have to use a 10% condition if we're sampling without replacement. And the word sampling is underlined, which hopefully clues you into the fact that if we have an experiment, if we're assigning treatments, then we don't actually have to use the 10% condition. We don't have to worry about independence. Third, we have normal. So if we have a dot plot of the residuals, the dot plot of those residuals should not have strong skew or outliers. Well, here's a look at the dot plot of the residuals. You can see that there is there's definitely not any outliers here. And it seems like there is a higher density of points right around -5. But there's nothing here that would stop me from doing a t-test. Remember, this is going to be a t-interval when we're all finished with this. So the dot plot looks normal enough for us to proceed. Next, equal standard deviations. So the residual plot cannot show a sideways Christmas tree, so it can't look like a triangle. So there is no triangle here in the residual plot, so we are okay with the equal standard deviations. And as far as random goes, we're looking for either an SRS or a random assignment of treatments. As it happens, the way we did this in class, we decided that this was a random assignment of treatments. Since my seating charts are not open seating, I actually assign seats. So let's go to construct the interval, the general formula for every interval. Point estimate plus and minus the margin of error. We'll take a look at this specific formula now. Here's our specific formula. We're looking at B plus or minus T star multiplied by SEB. Now you may notice here that almost every part of this specific formula can be read from the charts that we were looking at with yesterday's or the previous Stats Medic and its Check Your Understanding. B, of course, is the slope of the regression line. T star is the same T star that we've been using. And SEB is a number that we find in the chart. So a special note for you here on SEB, we're not actually going to have to calculate that, or on most cases, we're not going to have to calculate that. We're just going to read that directly from the chart. And certainly, in this example, we have our SEB is 1.33. So coming back down here, when we do the work, we have that the confidence interval is -1.517 plus or minus 2.048 multiplied by 1.33. Let's go over that 2.048 one more time. Over on the TI-84, the area that we're looking for is 1/2, 1 minus the confidence level. And degree of freedom, we said there were 30 coordinates minus 2. And then if we were to paste that and run that, surprise, surprise, we're going to get negative 2.048. Of course, all of our critical values are positive, so we don't use, no, I said critical value, I mean all of our T stars and all of our Z stars are positive. So that's why we have positive 2.48 multiplied by 1.33. Finally, we get to the conclusion, and it's the same conclusion that we always use. We are, well, 95% confidence that the interval from... Now, I actually forgot to calculate that margin of error earlier, so this will help us out for the conclusion again. Let's take the conclusion from the top. We are 95% confident that the interval from, well, now we have to compute negative 1.517 minus 2.724. So negative 4.24 to 1.21 captures the true, and in this case, it's the slope of the population LSRL between row and score. So we have to put in our explanatory and our response variables here. Let's read this one more time because I like the sound of it. We are 95% confident that the interval from negative 4.24 to 1.21 captures the true slope of the population LSRL between row and score. So I'm looking at this confidence interval and I see that part of it's positive and part of it's negative. So a special thing happens here, and this is a special bad thing. But if the 0 is a plausible value of the slope, then it's possible that row and score are not in a linear relationship. That's what that 0 slope means. So in other words, we can't actually, with this confidence interval, we cannot say that there is statistical evidence, convincing statistical evidence, that the row and the test score are linearly related. Okay, slope of 0 is a bad thing. Let's take a look at our important ideas next. We've got beta 1 in the state part. We have beta 1 is the true slope of the population LSRL. B1 is a statistic or the sample slope. For the plan part, which is learning target number 3, we have the name of the test is a 1 sample t interval for beta 1. Conditions are that linear conditions. We have a linear relationship. We have independence. We have a normal residuals. We have equal standard deviation. So that's that sideways Christmas tree thing we were talking about earlier. Residuals can't be getting bigger. Residuals can't be getting smaller. And finally, the observations must come from either an SRS or they have to come from a random assignment. And the last part here, which is confusingly learning target number 2, in the do part, we have the following formulas. The general formula is a point estimate plus or minus a margin of error. And the specific formula is beta B1, or just B, plus or minus T star multiplied by SEB, degree of freedom, N minus 2. So we are ready here for check your understanding. Everyone knows, obviously everyone knows, that cars and trucks lose value the more they are driven. So can we predict the price of a used Ford F-150 Super Crew? That's a very specific car make and model. Ford F-150 Super Crew 4x4 if we know how many miles are on the odometer. A random sample of 16 used Ford F-150 Super Crew 4x4s was selected from among those listed on sale at autotrader.com. The number of miles driven and the price were recorded for each of the trucks. Here is a sample, or here is some computer output from a least squares regression analysis of the data. Construct and interpret a 90% confidence interval for the slope of the regression line. Remember that phrase, construct and interpret means the four-part plan. Well, I don't think we're going to do a four-part plan here. This is all of the regression analysis. If I take a look, this does look like a linear relationship, you know. The least square, the residual plot over here in the middle, this definitely doesn't look like a sideways Christmas tree, and there doesn't seem to be a curve in it. And the residuals themselves, well, they don't look non-normal. Okay, there's no strong skew, there's no outliers. So it looks as though we would be ready to go with the liner conditions, or the liner conditions. Linear, of course, we talked about that. The scatter plot is in a line. And we talked about the residual plot doesn't show a curve. Independent, well, 10% rule, so there has to be more than 160 used Ford F-150, and I think that kind of makes sense. Normal, so the residual plot doesn't show skew or outlier. Equal standard deviation, the residual plot doesn't have a triangular shape to it. And finally, random, this came from a random sample. So the liner is all the way done. And I'm going to eat my words now because this there's nothing here. So we are going to have to do a 90% confidence intervals. Let's get started with that. State-wise, we have that beta 1 is a true slope of the population LSRL for miles, for price and miles driven. B1 we can find in our chart right about here, miles driven, and B1 is negative 0.16292. Confidence interval is 90%. That takes care of state. Let's plan. The name of our test is a one sample t interval for beta 1. The conditions starts with L. The scatter plot shows a linear pattern, and the residual plot does not show a curve. There's our R for our L for liner. For independent, our sample size 16 has to be less than 10% of all used Ford F-150s. And this seems true because there are more than 160 used Ford F-150s. So we're good with the I part. Remember that we have to use a 10% condition because we took a random sample, meaning this is not an experiment. Let's move to N, normal. So the scatter plot of those residuals does not show strong skew or outliers. I'm going to scroll up to take a look at that again. And actually, this isn't a scatter plot. This is a histogram. So let's go back and let's change that to histogram. But the histogram of the residuals doesn't show a strong skew or an outlier. Next, we have E for equal standard deviation. And our residual plot does not show a triangular pattern, so we're good there. Lastly, R for random. If you remember from the problem said that we had a random sample of 16 used Ford F-150s. Now I'm putting that in quotes because that comes directly from the problem. So that's the end of the plan part. Remember that your ticket for remembering all of those conditions, and that's a lot of them, is the word liner. Let's get to the do part. So this is the same do that we always work with. The general formula is a point estimate plus or minus a margin of error. Specific formula, B1 plus or minus T star multiplied by SEB. And degree of freedom is N minus 2. For the work, we have this negative 0.16292. That's our B1, and it comes from our chart right there. Next, we'll need a T star, so let's grab our calculator, and we'll go back to our inverse T. And we need a 90% confidence interval this time. So we'll change this to 0.5, 1 minus 90. We only have 16 coordinate pairs, so our DF is going to be 16 minus 2. Let's paste that in, and we get a T. Ooh, syntax, where did I make a mistake? 16 minus 2. I think that's it. We had the parenthesis in the wrong place. And it looks like it's thinking. There we go. 2.144. Oh, wait a minute. That was for a 95% confidence interval. And we only need a 90% confidence interval. So I'm going to hit that again. And remember that a 90% confidence interval should have a smaller T star since it is a smaller interval. Okay, so 1.761. 1.761 times, and then the next thing we need to do is look for SEB. Remember, you don't have to calculate SEB. It is in the chart right next to B, 0.03096. This works out to a confidence interval of negative 0.16292 plus or minus 0.05454. Finally, we can work on the conclusion together. We are 90% confident that the interval from negative 0.21744 to negative 0.10840 captures the true